So today we're going to finish with a random utility class. The general random utility model is going to be, our search is going to be for the analogous of a stochastic choice with menu variation of the axiom of the strong axiom of revealed preferences. Okay. So you knew that for discrete choice, if you have an access to a choice function, and if you have menu variation, what is the property that choices or choice functions will have to satisfy? Is the strong axiom of revealed preferences, right? So who remembers the strong axiom of revealed preferences, which is basically the version without indifference of the generalist, the GARP, right? The generalist axiom of revealed preferences. So can someone answer? Or I'm going to ask. So who remembers what is a SARP? So Alexis, can you hear me? Can Brice, so Alexis cannot hear me apparently. So Brice, can you hear me?
Yes.
Okay, can you remind us what is the strong axiom of revealed preference?
It means that you cannot have a cycle.
Sorry?
You cannot have this. If you have like a sequence of bundles, then you cannot have a cycle. If X is revealed perfect to S1 up to Sn, you cannot have Sn revealed perfect, strictly revealed perfect to X.
Okay. Yeah, so it means that if you have a sequence of direct revelation, x1 to x2, x2 to x3, and so on until xn, and then we have that xn is revealed preferred to x1, then this produces a cycle, right? Okay. Thanks. Now, okay. So now the question here is, so what about the random utility? So we learned previous class that we have this regularity property, right? So I think Eduardo noticed it. So what was the regularity property? So if you have a random utility model, then you have to have the following property, right? Which we call regularity. So if we have that, we have two menus, and one choice set is bigger than the other, more alternatives, then the probability of such an item X on the menu A has to be greater than or equal than the probability of the same item in the big menu. So in the smaller menus, the higher the probability of the same item. Okay, so now this is, I told you, this is kind of the weak axiom. Okay, but as opposed to the weak axiom to the warp, here there is not really a revelation of anything, right? Do you realize that? So it's just more a substitution pattern. So we say, if we throw more alternatives into a choice set, then because you are maximizing still a utility out of random utilities, right? Then this new item is possibly going to be the maximum according to some preferences relation, okay? So that means that you are not going to have, this probability of the original item is not going to improve. It only can decrease. So the more items you throw, so more competition, the less likely you are to pick the original item, right? So under utility maximization, there is only substitution. Do you agree? There cannot be complementarity, okay? So this is an implication, but it's not revelation of preference. So in a stochastic choice, my point being, it's very hard to get revelation of preferences, right? So it's harder. We're gonna see what to do, and we're gonna introduce this idea of the axiom of a stochastic revealed preference, which is the analogous of the SARP, okay? So consider X a finite choice set, and now consider a linear order on X, okay? So who remembers what's a linear order? So David, can you hear me?
Yes.
What's a linear order?
So basically, if you take like any linear combination of elements in that set, they are still in that set.
No. A linear order is basically a class of binary relation, right? So a linear order, right, means that you have what properties? You have to be complete, right? So you're a strict preference, right? You are reflexive. You're asymmetric and you're transitive, right?
I see.
Okay,
I
antisymmetric.
mixed up the definition, sorry.
Yeah, no, don't worry. So linear orders, okay? So consider a set of strict preferences, right, on X, and then basically we are going to put a distribution over these rankings, okay? So do you understand what I'm doing now? This sounds easy, right? I took 2 lines, but who can tell me what's going on here? So I'm going to create an example. So imagine my choice set. So let the choice set be AB, okay? Then what are the 2 possible linear orders or strict preferences here? So easy, right? Either A is better than B or B better than A, okay? So what is a random utility here? Who can tell me what is the pi? So basically it's pi of this, right?
1 minus pi.
Right. Okay, so this is greater than or equal than 0. Okay, that's it, right? So do you understand what's going on? Now, how many possible rankings there are there in 3 alternatives that are exactly basically linear orders over strict preferences?
8.
No, remember, the trick is n factorial. So
Oh, 6.
6, and you know,
6.
all of us are lazy, right? We're economists, so we are not going to. It's easy to to write them down, right? But there are 6 of them. Okay, so we have 6 of them. I'm not gonna write them explicitly, right? Yeah. So this is the 6 of them, and now a pi is now a vector of a 6-dimensional vector. Okay. Got it? So it's an element in the simplex here. So now, so again, the formula in general is n factorial. So you can see easily that as this set grows, then the more possible rankings I have. Okay. And then my random utility is basically this probability, is basically a probability over these rankings. So a particular random utility, for instance, is equal to 1/2, right? So at half of the time, I like A over B, and half of the time, I like B over A, okay? So this randomness is unspecified. The modeler doesn't know why this decision maker changes his or her mood. We just are looking for this number, the pi function, the pi vector, right? So we don't know it. So now the trick is that we want to see data, so stochastic choice, and we want to infer this pi, okay? So this is a cool problem, right? Because imagine what I'm telling you is the following, right? So basically, I'm going to see data. I have, first of all, menu variation. So I'm assuming I have an experiment where I'm changing the choices you see, okay? So I'm giving this population of individuals different alternatives, and I'm varying the alternatives, such as I expand the powers. Do you understand that? So I'm giving you many possible menus of options, okay? And then I ask you to choose from them. So then I compute the probability of choice, so the frequency or the share, depending on the interpretation. And then what is then the probability of picking alternative A, small a, in menu capital A? Or in this notation, rho sub capital A of A. What is then the probability? Well, I define this indicator function, right? That gives me 1 whenever the argument inside is true. And then this tells me that whenever A is better, so I'm using this notation here, which is a ranking, right? So you see the small r, okay? But let's change it so you don't get confused. but it's the same, right? So it doesn't matter which number I use, which symbol I use. But this is the preference relation, okay? So I have that. This is what it looks like. It looks like an expectation again, right? So it's basically the expectation of what? Of this indicator function. With respect to what random object? This object now is random, right? So I made it bold, but I guess I'm gonna make it like this so it looks random, because it doesn't look for you bold, right? So there's a wiggle on top. So this is an expectation of this indicator function. So this is what is my expectation of you picking A over B, right? A over all items, in fact. So A is the best according to this particular menu. So for this particular ranking in that menu. And this is the probability, right? So this is an expectation, okay? But another way to think about it is a mixture, right? So
You're
yeah.
summing the expectations here, or you're summing the what you're summing up here?
So this is basically the probability of each ranking. Sorry, so I didn't change this part. So thanks for noticing. So of course I have the probability of each ranking, and then the prediction of each ranking, right? This is 1 when the ranking predicts that A is the picked option, right? The chosen object, and then it's 0 if not. So now I'm going to tell you this, right? So from I ask you, do you prefer to switch to the to a asynchronous format? Yes or no? You know, I add also a third option. Nobody picks, so basically we have 2 options, right? So now 7 out of the people that answered said yes, and then 8 out of the people that answered say no. So that's another interpretation, right? So basically, if I sum of these 2 objects, right, I have the total number of cases, and then I compute a fraction of each of them, right? So this, some people prefer yes to no, the other people prefer no to yes, A to B, B to A, and then the relative frequencies of people are basically these pi's, okay? So you can see that we can also understand stochastic choice in this setup as a mixtures of individuals, right? So you're a mix of people that like the synchronous versus this, and then there is a fraction of you that don't like it, okay? And you know, all populations are mixed. We have heterogeneous preferences, you see? So another interpretation of random utility is this mixture of preferences, okay? Mixture of types. Okay, so who is going to vote for Donald Trump in the US versus Biden? So some people like Biden over Trump, other people like Trump over Biden, okay? So the fraction of people is going to give you the share, okay? So this is the most basic interpretation of random utility. Everyone understands? Okay. Now, we know
Right,
also, yeah.
So this utility that we get, for example, from the example you gave, that would be like a representative utility of one, like basically representative agent. Because it's you're taking the data from multiple people, right? So it wouldn't be one person's utility.
Yeah, that's a good question. But so think about it. So here, this is a different kind of aggregation. That's what I was telling you, right? So this is not really representative agents, because representative agents in the chapter 4 Mascolel is about average choice. Okay. So for instance, because in yes and no, it's not defined an average, right? Because you cannot take average of yes and no, right? It's a multinomial, is binomial, but it's basically is not quantitative. But for instance, in the world of commodities, you can take an average of commodities, right? The average demand. But here is different. So what we're doing here is counting types, okay? So for instance, some people, and this is the collection, we're just counting votes. So as in my survey, right? Some people pick yes over no, and we count the fraction of that type of people, right? So it's just we're creating the relative frequencies of types, okay? So, and then the final prediction is this average of these types. So this is called a mixture, okay? So the fraction of people that choose yes over no, right, is slightly above 50%. So let's say 60%, right? And the other is 40%. So as you can see, this is in fact an expectation. So it's an average. but it's not average. It's not average demand or average action, right? It's just the probability of choice, which is a share of people picking different alternatives, right? So this is a different kind of aggregate, which is an aggregate that makes sense, and that's why this substitutes the aggregate demand chapter 4, right? Okay, so good question. Now, so this is not representative because these are your actual preferences, right? We're just clustering you with the people that are like you, right? So type number 1, and then I count the fraction of you, and that's the probability of that type. Okay. Good. Any other question?
Yes. So if you don't mind explaining again, so the expectation that you have at the end of the
Yeah.
equation here. So the randomness is coming from this sort of preference variability, correct?
Yeah. So so you know that I can make a random object, right? If out of the collection of preferences with a pi, right? So that I have the support of this random function. So this is now a random function, right? So random preferences. So I'm not telling you. So you ask a little bit deeper, right? Is that where are these variation coming from, right? So we previously in this chapter, I told you that there is some sort of states of the world that are abstract, and then variation across these states of the world then gives you variation in this, right? But in particular, the key of random utility is that there are two interpretations. So in the population interpretation, it's just heterogeneity, okay? So some people like some things and other people like other things, right? So that means people like different things. That creates heterogeneity in preferences. And therefore, I can understand that heterogeneity as a random preference, okay? So therefore, the expectation over the random preferences gives me the probability of choice. Do you understand, David? But there is also the individual probability interpretation, which then tells you that yourself, right, as a consumer, have variability in preferences, right? So some days you like, ramen versus a meat pie. I don't know. And then the other days you like the meat pie over the ramen, right? Why? I don't know. And maybe I don't want to know, right? I just want to model it in a way that makes sense. Do you agree? So this can be modeled as unknown randomness, okay? So variability here comes from changes in your mood, right? Of what you like, cravings. Another interpretation of random utility in individual setups is mistakes, right? So you can say this guy really wants ramen over this, but then he didn't plan well, and then they closed the ramen place, so he had to eat a meat pie. Okay, so that's a mistake, right? And then that's a different thing that we're not going to call really random utility, but it can be modeled like random utility because it changes the ranking. So the key here is that randomness is a way to work mathematically with things that you don't understand. So when I say something is random, is I don't get it. Maybe I don't want to get it. It's too complex, right? So I just assume it's random, right? So that means something's changing, and then I have to model it. And then when given a structure, it means I'm trying to figure it out. But if you tell me from a neuroeconomics perspective, why do people have random preferences, right? Then maybe it's because your neurons are such that they don't collect exactly the correct information, and then you're trying to figure out what you really like, and this process is imperfect, right? And so your actual evaluation of reality is a stochastic process, and whenever it hits a barrier, it will choose the option A versus the option B. Okay, so that's a neuro explanation, a little bit more explaining why there is randomness, source of randomness. Now I'm not telling you the source of randomness, except that heterogeneity and mood variation. And that's actually a good way to do it for econ, right? Because in the end, we can just model these and try to make sense out of data. And in the end, we're going to get a model that is testable. And without specifying why you're random, we can still do something about it in the sense that we can model your behavior. Okay, do you understand? So that's the key. I don't need to understand your brain to still know substitution patterns. Do you get it?
I see. I guess my other issue was because when we see expectation over some sort of random variable, this is not, I guess, it's not the usual way or what we're used to seeing. So
Yeah, so, well, remember that according to our previous definition, right, we define basically these moods, right? So I can do the following, right, which is basically saying that, remember I defined this probability function over omegas, right? These are the moods, for instance, right, on this probabilistic space. So this is a completely, generic object here. And this probability now is going to be multiplied by this, which is the realization of this random omega. Okay, so these objects, all of them give the same answer. Okay, this is the expectation that I'm defining. Okay, with respect to the moods and whatever. In fact, this doesn't even need to be a sum, right? You can have an integral, in fact. Okay, so my only point is that these objects here, all of them give you the same probability. And as a little bit what Tyson said, is that in the end, because I have finite choices, irrespective of your moods, you are going to be ranking these two alternatives, either A is better than B or B better than A, right? So that means whatever moods you have, whatever source of randomness you have on the back, they are going to be projected to a finite many types. So in particular, how many of them? N factorial. So there's only N factorial ways that you can rank these alternatives, right? So whatever infinite randomness there is behind is going to be projected to finite randomness. And then, this means I can write this just with a summation over this finite collection of preferences. Got it? So it's the fact that there is only N factorial ways to rank alternatives, no matter what infinite source of randomness there is behind. So in the brain of decision makers, right? Mathematically, if you give me 3 alternatives, there is only 6 ways I can rank them. Okay? Got it?
Yep, thank you.
Okay, so now, so I'm going to tell you the axiom that is the analogous of the strong axiom. And I laugh a bit because it's so ugly that people, that's why I think theorists didn't like this model, because theorists are mainly mathematicians, right? I'm talking decision theorists, and they really like beautiful theorems and beautiful axioms. It's not really about explaining behavior. You would believe that, right? But it's really about the beauty of the math. So, that's the bias of our forefathers, right? Savage, they were mathematicians. So this axiom was kind of a slap in the face of decision theories because it's ugly, right? And, I think this is the most successful theory so far of the ones we have, but people kind of shy away from it originally back in the day in the 60s when psychologists kind of invented it because the axioms are so ugly, right? And so it took us almost 2 decades with McFadden to kind of come into terms with this. So, and this is the axiom, right? So it's the axiom of stochastic reveal preference. And this basically tells you that a probability choice, so this is the data, which means that I observe the choice probability for all alternatives in all the choice sets. This doesn't need to have full variation in choice sets. It needs to have partial variations in choices, right? So you don't need to have rich variation. Some variation is fine. So 2 menus is fine. Even only if for any sequence of alternatives and menus, right? So this is just pairs of alternatives, AK in menu DK, such that AK belongs to the menu DK. Then, and of course, DK belongs to the grand choice set X and is not empty. Then we have the following. If I take the summation or these probabilities of a small item AK in the menu capital DK over the sequence, right? This is in one of all sequence, right? So I can have infinite sequence. This has to be dominated by the maximum on what? On the set of all preference types. So I pick one ranking out of all preference types. So in the case of 2, I pick one of the 2, right? Either A is better than B or B is better than A. In the case of 3, is one of the 6, okay? is one of the 6. And then according to that, I start summing again the sequence, but only from the deterministic prediction. So this will be 1 whenever AK is the better item according to R in the menu decay. So this is 1 in that case, and a 0 otherwise. So if I take the summation over this, over the maximum, so the preference function that gives me the most numbers of 1s instead of 0s, this is going to dominate this alternative here. So, okay, so is that something that makes sense? Do you get some intuition like the SARP? Where is completeness, transitivity? Where is rationality here? So it turns out, by the way, that the axiom of stochastic reveal preference is equivalent to random utility with choice set variation. So that means this is the complete characterization of random utility, okay? So it's not only an implication, it's also sufficient. So if my data set passes this axiom, I can actually build a random utility back from it, okay?
Victor, could you please explain what is the object in the left side of inequality again?
In the left?
In the left side, yeah.
You mean this?
Yeah.
Yeah. So think of let's do an experiment, right? So you can see it. Okay. So let's do an example here. So imagine that I have an experiment with choice set 1 being equal to A1, A2, right? And then choice set 2 is equal to A1, A2, A3. Okay. Then what is my sequence of data? So my sequence of data is going to be basically a collection. So I can define one sequence. So let's define the following sequence. Okay, which is going to be A1 in D1, right? And then A1 in D2. Now, remember that the axiom, and now I'm going to compute the left-hand side. So this is a sequence with just 2 entries. So now the summation here is going to be the probability of basically here D1 of A1, right? Plus the probability D2, A2. Okay? And this is less than equal than this thing here, which is basically the max over the possible 2 rankings. Well, actually, here there are 6 rankings. And here you have the summation. Basically, I'm going to put a big parenthesis here. So you have this indicator function of the cases where A1, right, is better than A2, right? And here you have plus the indicator function of A1 better than AJ for J in 2 and 3. Okay? So this thing has to hold for random utility, okay? So like let's plug some numbers. So imagine that row D1 A1, right? I'm gonna make it violate regularity. So this is the same, sorry, this should be A1 here. Yeah. So this quantity, this is a small set, right? And now I'm going to make the probability of this less than the probability of D2 A1, right? So in fact, let this be 1/2 and this thing be 3/4. Okay. So this breaks regularity, right? So now can you verify using this thing that I wrote that this object will violate this inequality? Okay. So please do that. So let's plug the numbers. Right. So it's basically this is This is 2 fours plus 3 fours, right? We have 5 fours. Okay, and now this is more than 1, right? And I have to show that the right hand side will give me a number that is less than 1, right? So it will be at most 1. So here you have to pick some ranking out of the 6, right? Where at the same time A1 is better than A2, right? And then A1 is better than A2 and A3, right? So in particular here, well, basically you have this data set and you can plug it in and then you can check. So this axiom tells you that I don't think in this case it's violated, and because you can always find one ranking for which A1 is always at the top. So I will make this this part equal to 2, which is fine. But the axiom tells you that this should hold for all sequences, right? Not one sequence. So eventually we'll find one sequence for which this would fail, right? That's the theorem is telling you. But I hope you visualize what's going on, right? So basically this particular sequence, I can find, of course, one ranking such that A is the best. So this is fine. This passes, but there should be another sequence for which the ASRP fails because this data set violates regularity. Okay, so in other words, the ASRP implies regularity, but regularity does not imply it, right? Okay, so that's the axiom. So it's purely a combinatorial axiom. So do you think there is any value to that? Well, it's a little bit doubtful that it's useful for something, but it actually is a complete characterization. So mathematically it's good, and potentially you can create statistical tests to test random utility. Okay, so but I'm going to give you a better, hopefully better characterization of random utility. Okay, and this will have to do with trying to understand what random utility is doing. So motivated again by the question of Tyson. So this is about counting the fraction of different preference types, okay? And basically taking this average over those types. So I can create a matrix of predictions according to all possible types, okay? Do you agree? So this matrix is gonna tell you, basically it's gonna be defined by the following columns, right? So here in this matrix, each column, this is a matrix of ones and zeros. Each column in this matrix is a preference type, okay? So S is going to go from 1 to capital S. So capital S in general will be at most, the number of the n factorial, right? So here in particular, usually S is equal to the n factorial. So the size of this choice set when we assume full support, right? And so columns here are the preference types, and rows here are just the experiments. So you can see that they are indexed by k. So this is from 1 to n. So this is just the observations, okay? And then what I'm doing is basically I'm looking for the fractions of each types. So this is the pi that adds up to 1 is greater than equal than 0. And then I multiply this matrix, right, which is of dimensions n times s, right? And I multiply it by this thing that is s times 1, right? And I obtain here this object that is n times 1, okay? Got it? So let me write this as rho. Do you understand what's going on? So what I'm doing is basically I'm rewriting this expectation that you saw here right? In its matrix form. Got it? So this is just the scalar form of a matrix multiplication. So what is the matrix? Is this an entry here, right? This is the entry of the matrix. And this is just the vector multiplying the matrix. So now I index it in the following way. Columns are preference types. Rows are just the elements in the sequence of observations. Then I have the probability, which is indexed by the preference types. And then I have the output, which is the probability of choice in the sequence of data. And the observed data is equal to the multiplication of this matrix M times pi. Okay? So in other words, this is the expectation that we saw before. So the probability here is, of course, which should be like written with raw. The probability of A comma A is equal to this expectation. This is the scalar form. Okay, so now turns out that the axiom of stochastic reveal preference is equivalent to having a solution, at least one solution, to this system of equations. Okay? So this item 2 here is like the Alfred inequalities, right? This is something you can go into MATLAB and then compute. Do you agree? Okay. So I'm going to tell you an example in a bit. And then finally, right, this is equal to random utility. So we have a random utility rule that generates the data. And finally, there is also something else that is called the Bloch-Marshak polynomials that I'm not going to tell you right now, but I'm going to tell you in a second, or maybe I'm not going to tell you because this is more specialized. But it's basically an equivalent characterization of these 4 conditions. Now, the Bloch-Marshak polynomials, right, were the first ones to be invented somehow. And they are good to generate statistical tests because you can estimate these different rows and then put it in this sum and then basically have to check that these quantities here are greater than or equal than 0. So they lend themselves to statistical testing, and people have done it. The main issue with the Bloch-Marshak polynomials, which are the final item 4, is that they are really hard to use when data is not doesn't have the full menus. Okay, so it's less important right now. So we're going to focus basically on 2. So now I like this characterization 2 of random utility because it tells you really what it is. So it tells you random utility is really about finite mixtures. So if you take a finite choice set, compute all possible rankings, right? Create a matrix of ones and zeros, right? And then just look for the preference types probabilities that will explain the data. Okay? Now, this model cannot explain all possible data sets. I already told you, for instance, that this cannot be explained by a random utility rule. Okay? So let's do that. Okay?
Sorry, so this system equation will be solving for pi. That's what we'll be doing. Okay.
Yeah. So Tyson, again, he's right. So pi is the proportion over types, right? So the fraction of each type. So I'm looking at a mixture of types, right? That explains the data, if any. That's the key. Not every data set can be explained. Okay? So this is a testable implication. Now it turns out it's of course sufficient because if I find the pi, I found the random utility. Okay? Got it? So I'm going to prove basically that 3, which is random utility, implies the axiom of stochastic reveal preference. So this one is super easy. I just take the definition of random utility, which is the fact that inside this summation over the sequence of data, I have my expectation, right? This is the expectation over preference types of this indicator function. Now, notice that if I maximize over the probability type here, this has to be an upper bound, right? Because it's the maximum. So if you maximize something that is linear, then the maximum is going to happen at the extremes, right? We already had a description in the previous class with a drawing, right? So if you are maximizing a linear function, then you're going to end up with solutions in the extreme points. So that means that the maximum of this thing happens with probability mass 1 in one ranking, right? So this will happen here at a particular ranking, okay? So now the maximum will happen here, and this will be the upper bound of this summation of probabilities. So that was easy, right? So it turns out that proving that random utility implies the axiom of stochastic reveal preference is very easy, okay? Now, I need to show that this thing implies random utility. So I'm going to do it in the following way. So I'm going to now prove that if you satisfy if 3 holds, so which is the axiom of stochastic reveal preference, sorry, this is 1. This implies that there is a solution for the system of equations 2, okay? Okay, so this actually is a corollary of something called Farkas lemma, or the theory of the alternative, theorem of the alternative. Okay, so the theorem of the alternative tells you that for every linear system of equations, in this case, m pi equal to rho, right? There is an associated linear system of inequalities, okay? That is m prime y greater than or equal than 0 for some y, right? Vector, such that if m prime y, so this is solving over y, has a solution, then m pi rho does not have a solution. That's why it's the alternative. And this is, in fact, is not only then, but is if and only if. Okay? So ASRP means that the inequality has a solution, okay? Which implies, sorry, inequality cannot have a solution, which implies that m pi equal to rho has a solution, okay? So verifying this is tedious, and I'm going to send you a link with what Border did. He has a long proof of 1 page trying to show why the ASRP shows that this alternate problem of inequalities doesn't have a solution, right? And therefore, this means that the original problem, the system of equalities, the m times pi equal to rho, has a solution, okay? So basically, this is an application of Farkas lemma. So once you have that 2 holds, then 2 implies random utility, right? Which is 1. Okay. So we close the circle here because 1 implies ASRP. ASRP implies the linear system of inequalities, and the linear system of inequalities implies random utility. And we go back, right? The only thing I haven't proved is the Bloch-Marshaks, which I'm going to leave outside for this class. But it's important that you have it if you need it, in case some literature tells you that. But Bloch-Marshaks polynomials are being used less because they need full menu variation, okay? None of them have an interpretation, except really for this item number 2, which tells you that random utility is finite mixtures, okay? That's the kind of abstract inequality interpretation. So I'm gonna stop here. So 5 minutes, and then we come back, okay? So let's conclude this particular section by making a connection with chapter 4. So I ask you to read for the problem set chapter 4, about the aggregation power of consumers. And one key result there is that if you compute average demand, so mean demand in the commodity world, then turns out that average demand doesn't have to come from utility maximization, right? So rationality doesn't aggregate in the sense of chapter 4. Now, so that means if you have two demand systems generated each by a rational consumer, the average of the two cannot have, it may not have, more than cannot, may not have the properties of rationality, right? So it can violate, for instance, the Weak axiom. So that's very, very bad. So that means basically that macro, for instance, if you do representative agent, if you want to believe the story that you are micro-founded, you cannot have both, right? So you cannot have both micro-foundations and representative agent. Only under very stringent properties over preferences you can have that. Okay, so that's chapter 4 for you. Now, so is that the end of macro? Well, not really, right? So you only need to think of the correct primitive. So you need to think about heterogeneity using random utility. That's the correct way to do it. And that's what people in IO and in the rest of things have been doing for a while, and now macro people as well. So macro people are doing what is called heterogeneous agents, okay? Which is a form of random utility, okay? Heterogeneity is what gives you randomness. Shares, okay? So it turns out also that a random utility is so nice that actually it also aggregates. So imagine I have a collection of individuals, each of them random utility. So I have all the viewers or subscribers to Netflix, okay? So all of you have random preferences over Netflix movies or types of categories, right? So it's not that you have a fixed preference, right? You're changing. So now the question is, if I take the share of people that like the new movie added to the Netflix catalog, can I still model this as random utility, right? It's an aggregation result, right? Turns out that yes. So this is the result. So there exists a representative random consumer that basically is random utility. So in other words, there exists a random utility rule such that this will explain the data, which this is the market share, right? So I use an M here, the market share, okay, is equal to this probability. So I start, for instance, with these probabilities of behavior, and each of them is ruled by a random utility. So now I can have a measure over vectors, over preferences, right? So this is a measure over measures, this mu, okay? And then I am going to use the proof. I'm going to omit it because it's just a follow-up of these block Marchaks, and that's the only way I put them there. So this is just an observation I want to see. The proof is super simple. So I just apply these block Marshak polynomials and exchange summations. So it's super trivial. And then it turns out that by doing this, you can prove that if you have a collection of random utility guys, the aggregation of their behavior and the market share generated by these guys is also random utility, okay? And then, yeah, so this is very cool. So now random utility, even if you're random utility at the individual level, you can also have random utility at the aggregate level, okay? So we can move from individual stochastic choice that usually we don't have data to aggregate the stochastic choice, which is market shares, which we usually have better data, okay? Got it? So yeah, that's why random utility is way better than the standard model. And now let's see why people use it. And so this is the next section, which is a new section, by the way. And this is called discrete choice with attributes. So in applications, usually the choice is unobserved. So, you know, as you can see, decision theory is in this tension between what data do we have and what we should have, right? So, and the primitive of the previous subsection was a primitive only for experimental economies. So we can run experiments where you change the availability of alternatives. So we have all possible menus, okay? This is an experiment. This kind of data exists mostly in experiments. It's very difficult to have choice set variation in real life. That means in markets. So in contrast, what happens in real life is that people have a fixed choice. So imagine tomorrow you are hired to estimate basically the demand of used cars in London. So is there really choice variation for a fixed slice of time, right? So fix this particular year, the previous year, right? Fix 2019. Is there really a choice set variation in cars? Very unlikely, right? So you're going to have more or less the same kind of alternatives or cars, models, makes, and so on. And this is going to be the fixed choice set of alternatives, capital A. Okay, and we're going to assume it's finite. So it's finite, but more important, it's fixed. So here in this chapter, there is no longer choice set variation. Okay, so we're going to study what can we say about random utility in this framework. So this is the econometrician's hat. Now, the utility of alternative A, because we don't have choice set variation, we have to think of attributes. Okay, so this is more like chapter 3. So what did we have in chapter 3 to be able to study demand, even if we didn't have choice set variation? Because the number of goods stay the same, right? We have price variation, right? So we have budgets. Here we don't have budgets, but we can have these kind of quasi-linear budgets. But in general, what you really have is attributes, okay? So attributes also cover more general random utility, like for instance, voting. So in voting, you don't really have a budget, right? So you either pick Biden or Trump or Biden, and then it's really about attributes of the candidates, right? So what policies do they like and so on. So for instance, for consumption, X attributes can be, for instance, price, can be color, quality. So how many how many doors your car has? Is an SUV? Is does it include four-wheel drive or not? Right. So this is a set of attributes, and we have a vector of observable attributes, and we acknowledge that there may be unobservable attributes. And then we take this collection of all observable attributes indexed by the alternative to be what is called the observable profile, which is, in the case, these are scalars, this is a vector, right? But in general, it can be a matrix, right? Do you understand? So X without a subscript is the collection of all attributes over all alternatives. X with a subscript is the collection of attributes, observable attributes for that particular alternative. So what are attributes for the car is color, mileage, consumption of gasoline, quality, and number of doors. Does it have AC and so on? Okay, got it? That's all the data that you observe. Now, random utility here for an alternative A given attributes X is going to be equal to a deterministic mean utility, which is that varies with the menu, with the alternative and with a set of observable alternatives, and then a shock. Epsilon is a stochastic shock to preferences, which is interpreted as an observable attributes mainly. This is going to be our main interpretation of this shock. So this term here is random. This thing here is random. The thing in the middle, the V, is not random. Okay, this is deterministic. Understood? So in my leaks and in the PDF is a bold symbol, right? So in terms of random utility interpretation, we can use states to define this extended state space when you have the joint probability over omegas, which is the unobservable attributes, and X, which are the observable attributes. And then we can define here this probability. Okay. So in other words, now there is randomness because of the whole vector of attributes, which is a mix of an observable attributes omega and observable attributes X. Do you get it? So for instance, if you see a car, so you guys know about these Westphalias, for instance, cars, right? So these combis, these are really cool cars, right? That if you look at characteristics, they are really bad in general, really bad cars, but people like them, right? Because they look cute, I guess. That's an observable attribute, right? It's very hard to measure. Some people really like that car. So some people, have a car that is of a particular color, has a nice sticker that they really relate to, and they like it, right? As an econometrician, I cannot know all the attributes that people look into a car. Maybe they like the seller. Is a good salesman, right? That sell you that car, and therefore that's the hidden attribute there, right? That is sold by this particular salesman. So there is always unobservable attributes, and these are captured by this omega, okay? And randomness comes because of the variation in observable attributes, conditional on the observable attributes. So conditional on observable attributes, you're still random, okay? Because epsilon changes. This is capturing the unobservable attributes. Got it? So in principle, it depends on the observable attributes, in principle. Then we're gonna play it and make it independent. But right now, no, okay? So next thing is defining what is.
So unobservable attributes are included in the error as for the moment.
Yeah, that's the assumption, right? So you were basically assuming this is additive.
Yeah.
So the observable part enters through the mean utility, which is deterministic, and then you have an extra term, which is unobservable attributes. So it's additive separability. So great.
I don't really understand how the omega, so the omega part there. So that's within the error, I guess.
Yeah, so let me write the definition so you understand it, right? I haven't written it. Yeah, so that's why. So what we have here is that a discrete choice with attribute representation basically has a discrete choice attribute representation if there exists a deterministic utility which takes values on the product of item attribute for the item and goes to reals. This is the mean utility, right? And a probability space that is basically a probability measure over the all vector of attributes, including unobserved attributes, such that the probability of alternative A given observable attributes X is equal to the probability over the unobservable attributes, the omegas, such that the utility experience of alternative A given observable and unobservable attributes is the top of the rank, right? So because epsilon is random, this is basically changing with omega. So here I'm conditioning omega and then taking the measure over all omegas such that this happens, right? So this means A is the one that maximizes utility. Understood? So alternative A for some realizations of omega is the top alternative, okay? In the realized utility. Therefore, I'm just taking the probability over all the moods or all the unobservable attributes that make A the top alternative. Okay? Understood?
Is A unique or A can be?
Here we're assuming uniqueness. So we're assuming strict preferences. In discrete choice, basically this will mean that epsilon has a smooth density without atoms. And that's enough to have that ties of utilities are going to be events with zero probability. Okay, Schumann? So basically, if you have a density with no atoms, we have a density, a PDF, no atoms, then this is enough to claim that almost surely there is no ties, no indifference. So here we can do without indifferences.
And here the random utility function is linear, right? We are assuming linear utility.
Yeah, so this is interesting. So right now, it turns out that this representation is super general because epsilon can be anything at this stage, right? And in particular, this is called additive random utility because we're assuming this separability of an observable attributes utility and the observable attributes utility. So this is kind of this structural assumption, but because epsilon is so general, in principle, you can express everything you can with random utility here, right? And then in order to estimate these models, we are going to put more assumptions, and then it's going to become a special case of random utility, okay? But right now it's super general. It actually has no content. We have to put additional conditions, okay? So it's too general at this stage. So first assumption that sometimes people do to be able to estimate it in real life is that the epsilon shocks are independent from observable attributes. If they're independent, that means that, for instance, what Schumann said is true. There is this additive structure where it creates this separability. And this, of course, makes this thing a special case of random utility. So that means there are some models in random utility that cannot be covered by this. Now, remember, right, that we are going to have this assumption of exogeneity. So epsilon is independent from the observable shocks, can fail. For instance, if you have firms that take into account the shocks to preferences to change prices, and if X has prices as attributes, then it may happen that X and epsilons are related, okay? And then you don't have these independence assumptions. So people have considered these extensions, but for this particular section, we're going to study the case of independence, right? Separability. Now, I'm going to tell you even a simpler model, which is what econometricians use, which is called the simple attributes model, okay? And this basically is going to tell you that you observe the actual utility, so you know the utility. So that means up to a parameter, right? Without loss of generality, imagine you estimate this parameter, so you know the utility. This is equal to the multiplication of this vector of attributes times a beta factor, okay? Beta is just a mix numbers that mix these attributes and then generates a linear index, which gives you the numerical number that is your mean utility. So, so now, as you can see, this function doesn't depend on A anymore, but it just depends on the attribute vector. So for instance, if you have two goods that have the same price, and price is the only attribute, then they both have the same utility, the mean utility. Okay, understood? Okay, now, so here we are allowing this kind of beta thing, but in particular, we can basically make it so it doesn't depend on A, right? Basically, we can make it such that beta doesn't depend on A as well. So it's even simpler, okay? So in this simple discrete choice model, we have basically that the probability of A conditional on observable attributes X is equal to this X A times beta plus epsilon A is equal to the max of this of the other probability. So this is going to be the one that maximizes utility, okay? And this is the usual discrete choice model that you see with the class in Nail, for instance, Nail's class. So everyone understands what's going on. So it's as before, but with the additional assumption that you know the mean utility, okay? And beta is fixed now. So what do people do with this kind of models? So you basically try to look for market shares conditional on attributes. So I go to the data in London and I see the fraction of people that bought Honda Civics with this price tag, with this mileage, with this efficiency of gas consumption, and so on, right? So conditional on that set of vectors, I compute this share. And that's my data set, right? So then I have this observation for all prices, and I can use it to estimate my model. So I want to estimate beta. So in order to estimate beta, usually what people do is I assume epsilon and x are independent. And then I also assume some distribution for epsilon, okay? So I fix the distribution of epsilon, like the example of the logit, right? So epsilon is a logit. Then I can just estimate this very easily from the data. And that's why logit is so popular, okay? And then you also did it in the you're going to do in the problem set the probit, right? That's another model that people use. Now, okay.
So if you change the distribution of epsilon, you'll have different answers, right?
Yeah, that's the key, right? And a little bit the question is there something you can do without assuming the distribution of epsilon, right? And the answer is yes, you can do something if you have choice set variation, right? So if you combine this information, for instance, that we have with choice set variation, then you can estimate epsilon. There are a lot of things that you can do, but this is an econometrician's problem, right? So identification, I'm not going to deal with. I'm just telling you the model, okay? But yeah, it's a good question, Sean. So people usually can do something without assuming epsilon. But what people have done historically is assume some epsilon, right? Because it's easier, okay? Now, okay, so now let's do the consumer theory part with discrete choice, which is fun. So right now we're going to take the interpretation of shocks to just unobservable attributes. So now fix a menu, and then I can compute what is called the average consumer surplus under random utility. So we can estimate the expected welfare of an individual. So this is random utility, and then I take the expectation of the utility you experience when you maximize. And this gives me what is called the consumer surplus, okay? This is the object I define. Now for discrete choice, and this discrete choice, the simple discrete choice, which is the simpler version, I do the same. And now because the choice set is fixed, it's really the surplus I get for this set of observable attributes, right? So this is the expected welfare I get for this price tag, for this mileage, for this kilometer efficiency with gas consumption. So what is this? Is the expectation of the experience utility over all possible alternatives when epsilon is random. Okay, so given the unobservable attributes, what will be your expected welfare? Got it? So this object is just a definition, right? It's just an expectation. Now, turns out that I can actually define a Roy's identity for this. Okay, so this object here is the indirect utility, right? So imagine, for instance, the only attribute is prices. Then this is the indirect utility for a price vector. Got it? Okay. Now the question is, remember that the whole point about doing utility maximization in the deterministic chapter was that you can get this reduction of dimensionality, right? So everything can come from deriving a single utility function, okay? The indirect utility function. That was the Roy's identity. So you derive, and I'm 3 minutes late, so I'm going to finish with this. So you derive the indirect utility with respect to prices, and then you obtain the demand vector, okay? That was chapter 3, Mascola. So here, turns out it's the same. Look at the entry number 3. So if I take the indirect utility, here is not longer indirect utility, right? It's called consumer surplus function. And this is a function of attributes, right? In particular, for instance, this is a function of x, right? So this is the gradient with respect to that vector. Then, so this is the correct notation. So that means this will give you the choice vector, okay? So it turns out it's the same. We are doing the same as before. We are reducing dimensionality, okay? So I'm going to stop the class now.